right, we talked about at the beginning of this chapter that there were lots of times that we would need to find an absolute maximum or minimum, and we have learned methods for how to do that, and we've talked about all different types of real world scenarios where that's relevant. And so we're going to hit some word problems today where we need to do exactly that. We need to maximize a profit. We need to minimize a cost of manufacturing something. We need to maximize the amount of an area or a volume that we can get out of an amount of space that we have. Those types of scenarios. When I'm working with word problems, let alone calculus word problems, it always seems like a daunting task. So they give me some really great suggestions on page 277. Number one, it says the first step is read the problem until you understand it. If you need to read it a couple of times, do that. And ask yourself, what are you trying to find? What you are trying to find is almost always in the last sentence of the paragraph for the word problem. So that's a really good place to look once you've read the whole thing and you're going back through. Look in that last sentence because that usually tells you what you're trying to find. Then number two, draw a picture. In word problems, a picture is worth 1,000 words. Number three, introduce notation. Assign a symbol to the quantity that's supposed to be maximized or minimized. They're going to call it Q for quantity here, but like if you're trying to maximize your area, you could call it A. If you're trying to minimize your cost, you could call it C. Okay? They're going to call it Q generically for quantity here in the description. So assign a variable to the quantity that you're trying to maximize or minimize. That's what you would have gotten out of the last sentence of the paragraph, what you're trying to find. And then also assign symbols for any other unknown quantities that they give you in the word problem. And if you can label them on the picture that you drew, that's great as well. And they do suggest that you use like A for area, H for height, T for time, things that would be reasonable for you. Number four, express Q, that quantity you're trying to maximize or minimize. Express that in terms of some of the other symbols. So basically create an equation for what you're trying to maximize or minimize, and don't create some equation that has nothing to do with the other information in the problem, right? I mean, express it in terms of what you're given. And then number five, if the quantity that you're trying to maximize or minimize has been expressed as a function of more than one variable, like let's say that you're given volume and you've got volume is equal to length times width times height. You're not going to be able to go through and take the derivative of that and find critical numbers and find maximums and minimums with three unknowns, right? You can only have one unknown. So you're going to need to go back if your quantity that you're trying to maximize or minimize has been expressed as a function of more than one variable, then use the information that's given to you in your problem to find other equations that you can use to eliminate all but one of the variables, so that when you're done, you have that quantity that you're trying to maximize or minimize written as a function of only one variable. Then you can go back and use the methods that we already know for finding absolute maximums and minimums. Yeah, but that was like 3 weeks ago and I don't remember any of that. Okay, well, let's think about it for a second. If you're trying to find an absolute maximum or minimum, it can occur at a relative maximum or minimum, or it can occur at an endpoint, right? So how do you find relative maximums and minimums? What do you do first? Oh, it's worse than we thought, right? Yes, critical numbers set the derivative equal to 0. Yes. So you're going to look for where you have critical numbers, where your derivative equals 0 or where your derivative doesn't exist. And then you have to make a sign graph for those, because just because it's a critical number doesn't mean it's going to be the relative maximum or minimum that you're looking for, right? So we'll make a sign graph and we'll check to see, is it a relative maximum or minimum, or what is it? And then we'll also need to check our endpoints, because the maximums and minimums can occur at endpoints if I happen to have endpoints. Sometimes I will, sometimes I won't. It just depends on my word problem. Okay? Enough talking, more doing. So page 278, example 1. A farmer has 2,400 feet of fencing, and he wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. So what are the dimensions of the field that has the largest area. All right, I'm going to read that problem until I understand it, and then I'm going to go back and look for what am I trying to find, because I'm supposed to be either maximizing or minimizing something. So what am I trying to find? We said it was usually the last sentence in the paragraph, right? Yes. What are the dimensions that have the largest area? So I am trying to maximize the area. All right, so number one, I've read the problem until I understand it. Specifically, what am I trying to find? All right. Number two, draw a handy dandy picture. So I can go through and say, okay, if I'm trying to draw a picture of this thing, they told me that I had a rectangular pen and it was along a river. So here's my rectangular pen. I don't need any fencing over here. So I'll have a width here, and a length here. All right, number three, it says assign a symbol to the quantity that's supposed to be maximized. Let's call it A for area. And also select symbols for other quantities in the problem. So we've identified length and width. And it says put those on your diagram as well. So, okay, we've done that. Number four, express that quantity you're trying to maximize, in our case the area, in terms of some of the other symbols from the problem. So, if I'm trying to find area of a rectangle, what is that? Length times width, right. So, sometimes area would be length times width, sometimes it would be base times height. If you've labeled yours with length and width, then you would want to express it in terms of some of the other things that you've used in the problem. There are sometimes that there are multiple formulas for something, like we've seen multiple area formulas for a triangle, whether it depends on whether you know the sides or whether you know the angles or whatever. In that case, you would want to base it on the information that you have in the problem. All right. Then, number five, it says, if your formula that you just created has been expressed as a function of more than one variable. Right now, our area is in terms of length and width. I can't leave it that way. It has to be expressed in terms of only one unknown. Then I'm going to have to go back to this problem and find some other information in this problem that I could use to replace either length or width. So I'm going to go back to my problem and say, okay, there were 2,400 feet of fencing, right? I got to be able to use that somehow. So what's the 2,400 going to be equal to? Yeah, the two W's and the L, right. So I have 2,400 feet of fencing to use here. So I could say W plus L, or 2W plus L, has got to be equal to the 2,400 feet of fencing. Now it's just like having a system of two equations with two unknowns, right? If you're trying to solve, you can solve one of the equations for one of the unknowns and substitute it into the other equation. That's all we're doing. It's just right back to Algebra 1, basically. All right, so I'm trying to get my area formula in terms of either L or W. Therefore, it doesn't matter which one I replace, right? So work smarter, not harder. Is it easier to solve for L or solve for W? If I solve for W, what do I create? Fractions. Oh, I love fractions, right? If I solve for L, I don't create fractions. I'm going to avoid fractions if I can. So I'm going to go through and solve for L. It doesn't matter which one you solve for, you get the same answer, but I'm just going to make my life a little easier here. So then I can replace L in my formula with what we just found out it was equal to, 2,400 minus 2W. And then it's still being multiplied by the width. So you could simplify that if you want to. While you're jotting that down, we did optimization problems in pre-cal, you might remember. But all the ones that they gave us in pre-cal, they had to give me a parabola. Because we knew the maximum or the minimum had to occur at the vertex, and we knew how to find the vertex of a parabola, negative b over 2a. But when they gave me something that maybe looked like this, that was something like a cubic or a quartic or something, I didn't have an algebraic way of solving that. I could use the max or min button on my calculator, was about all I could do. And so now we can take that concept that we learned in pre-cal and step it up, because now we do know how to find absolute maximums and minimums using our first derivative test. All right. So now that we've got the equation for our area, we said that our absolute maximum could come from our critical numbers, or it could come from our endpoints. So let's think about endpoints for a second, because we said sometimes we would have them and sometimes we wouldn't. It would depend on the problem. When I'm trying to find those endpoints, the reason that I've waited is because I needed to create an equation in terms of one unknown, because I am looking for the endpoints of that one unknown. I'm looking for, in essence, the domain of W. So what is the smallest value that W could be? Can it be negative? Can you have a negative width? No. So what's the smallest value it could be? It could be 0, yes. So that's going to be my endpoint, that it could be 0. What is the largest value that it could be? I got 2,400 feet of fencing. What's the largest value that it could be? 1,200. If I use none at all for the length, I'd have to divide the 2,400 between the two widths. Now, I understand that both of those scenarios are preposterous, right? No farmer is going to use all 2,400 feet of fencing and lay it right there beside the river and have the fencing right beside the river and encompass no area, right? And no farmer is going to put 1,200 here and then another 1,200 right beside it and have no length at all and encompass no area. I get that. But remember, for AP intents and purposes, if you are working on a closed interval, you must show that you considered those endpoints to pick up. If that portion of the FRQ is worth 3 points, you're going to lose 1 point if you don't show that you considered the endpoints in terms of your absolute maximum and minimum. Okay, so even though we know that that's a ridiculous scenario and it would give us an area of 0, we are going to need to consider that in our final answer for that reason. Okay, so critical numbers. How do we find critical numbers? Set the derivative equal to 0. So let's take the derivative. So what's the derivative of 2,400 W? 2,400. And what's the derivative of 2W squared? 4W. So 2,400 minus 4W is set equal to 0. How do we solve that? All right. Okay, either move the 2,400 or the 4W to the other side, either one, whichever you prefer, and then divide out that coefficient on the W. So we'll get W as 600. Just because it's a critical number does not mean it has to be a relative maximum or minimum, right? I got to test it. So let's do our first derivative test. I'm going to make a sign graph. Just good practice for us to label our sign graph with what it's the graph of. This is the graph of our derivative, so that it's clear to me if I'm looking back over my work later on, or it's clear to the grader if there's somebody looking at my work. All right, so I've got the one critical number down here at 600. So let's pick a test point. I'm going to plug 0 in. That would be an easy value to use. What do I plug 0 into, the original or the derivative? Derivative, right, because I'm making a sign graph for the derivative. I'm trying to figure out where the derivative is positive or negative. I plug it into the derivative. So I'm going to plug 0 in and I'll get a positive value. Cross a single critical number and the sign's going to change. I could also pick a test point in that interval if I wanted to. So what occurs when the derivative changes from positive to negative? I'm going to have a relative maximum there, right? So I'm going to have a relative maximum at 600. If they don't say justify my answer, I'm not going to write any more than that. But what if they say justify your answer? What do you have to write? Literally write out in sentence form. What do you have to write? What? Yeah, I have to write out what the first derivative test says, which is what? What's my justification here? All right, so I literally have to state that On this interval, the derivative was positive. On this interval, the derivative was negative. Therefore, there's a relative maximum at 600. So I have to state, when W is less than 600, my function is positive. When my derivative is positive. When W is greater than 600, my derivative is negative. Therefore, since the derivative changed from positive to negative at 600, I have a relative maximum there. I have to write it out in that way. The sign graph, remember that handout I gave you, the sign graph is not enough. All right, so I have a relative maximum at 600, but that is not my maximum value. How do I find the maximum value? Plug it in to what? The original or the derivative? The original. It is the maximum of the original. So I'm going to take W is 600, and I'm going to come back up here to my original equation for area and plug in that 600. So if I do 2,400 times 600 minus 2 times 600 squared, I'll get 720,000. So I would have a maximum area of 720,000 when my width is 600. All right, now again, we have to check those endpoints. Even though we know they're stupid and we know that when we plug in either of those values, we're going to get an area of 0. Literally, it's going to take me 10 seconds to write this down on my paper, and I'm going to pick up an extra point for it. Okay, so it's worth it for us to do that, just for them to see, yes, I did consider my endpoints. So when I compare 0, 0, and 720,000, I think the farmer might be a little happier with the 720,000 fenced-in area. All right, the other thing with word problems I need to be careful of is that I answer the question that's asked. Because if I circle 720,000, that is not the answer. If I go back and look at the problem, it didn't say what is the maximum area that gets fenced in. It says, what are the dimensions of the field that give me that maximum area? What do they want? The length and the width, right. So we've already got our width is equal to 600. We're going to need to go back and find our length. Luckily, we have a formula right up here for our length. So we can say, okay, our length is 2,400 minus 2W. I already know W is 600, so let's just plug that in. So if my length is 2,400 minus 2W and I plug in 600 for W, then I'll get 1,200. So the answer that I want to give here are the dimensions, 600 feet by 1,200 feet. And of course, you could use common sense to get that as well. You don't have to plug back into the formula. If you're coming back up here and going 600 here, 600 here, that would leave 1,200 here. That's fine. All right, let's look at another example. Example number 2, now that we kind of have the feel for those steps that we're using, we'll go through this one a little more straightforward. So, example 2, it says a cylindrical can is to be made to hold 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. All right, so you're going to read the problem until you understand it and until you figure out what you're trying to find. What are you trying to find? Find the dimensions that will minimize the cost of the metal to manufacture the can. What am I trying to find? I am trying to find the minimum, but yes, the minimum of what? Surface area. When I read a problem like that where I'm like looking at a cylindrical can, I'm thinking like Coke can kind of thing. I'm thinking cylindrical can, I automatically jump to volume. I just automatically want to start calculating the volume. That's not what they're asking for here. They don't want to minimize the amount of oil they can put in the can. Or they don't want to maximize the amount of oil that they can put in the can. They want to minimize how much it costs to produce the container that holds the oil. That's the surface area of that figure. Now, on the AP exam, remember, sometimes they'll give you formulas, sometimes they won't. I would not give you either of these formulas. I would not give you surface area of a cylindrical can or volume of a cylindrical can, because that's something that you can figure out on your own using very basic formulas from middle school math that you should be able to do. So let's go through that together, okay? So if I'm trying to find the surface area, all right, let's think about this can over here. I've got the bottom and the top, which are both circles. So what's area of a circle? Pi r squared. So I'm going to have 2 pi r squared for the top and the bottom of the can. Okay, but where does this 2 pi r h come from? All right, think about this for just a second. If I were to take a knife and cut down the side of this can and unroll it, it's kind of easier to envision if you like take a piece of paper and you roll it up into the shape of that cylindrical can. Okay, so if you take that piece of paper, you roll it up like that cylindrical can. If you were to slice down and unroll that, you get a rectangle, right? So when I'm trying to calculate the surface area and I'm thinking about what it's going to take to go around this thing, not the top and the bottom, but what it's going to take to go around it. If I slice down this side and I unrolled that, I would get a rectangle. Area of a rectangle is length or times width, or base times height, however you want to think about that. All right. If you are thinking of the base, what is that base? It's, if I unroll that circle, what is that? Circumference, yes. So circumference is 2 pi r, and then the height of your rectangle is just the height of your can. So if I take this cylinder, I slice it open, I unroll it, I get a rectangle. The top of that rectangle comes from the circumference, and then the height of that rectangle is the height of the can. So circumference, 2 pi r times h, base times height, okay? So that's where we get the surface area formula. That's what we are trying to minimize. If I'm going to minimize that, remember that I'm going to take the derivative of it. I'm only allowed to have it in terms of one unknown, and right now I have it in terms of r and h. You've got to get rid of one of those. There has to be some information in this problem that I could use. So they told me in this problem that volume was equal to 1 liter or 1,000 centimeters cubed. All right, so I also then need to be able to come up with the volume formula. If you have a right figure is one that it's the same shape at the bottom as it is on the top and it's perpendicular to its base. So again, when we're thinking about this Coke can, I've got a circle at the top, circle at the bottom, perpendicular to the surface that it's sitting on. That's a right figure. The volume of a right figure is always going to be area of the base times the height. I mean, think about a box, right? For a box, the area of its base, it's a rectangle. So it's just length times width, and then you multiply that times the height, and sure enough, that's the volume formula for any type of a, like a box that you might have. So same story here. Area of the base, what's the base of our figure? Circle, so what's area of a circle? Pi r squared, so our volume's just going to be pi r squared times h. So they told me that my volume was 1,000, so I can say, okay, 1,000 is equal to pi r squared h. So again, on the AP exam, they might give you those formulas, they might not. I would expect you to be able to generate those because all we needed to generate them was area of a circle, circumference, and area of a rectangle, right? And just putting those things in combination. Okay, so we've got to replace either r or h. Which is going to be easier to do, solve for r or solve for h? Because I can do either, right? Solve for h. If I solve for r, what am I going to get? Radical. Look. So definitely solve for h. Work smarter, not harder. So divide both sides by pi r squared, and I'll have what h is equal to, and then I can plug that into my other equation. So that I am creating the equation for the area in terms of only one unknown. All right, let's simplify that before we start trying to take derivatives of it. We could say the 2 times 1,000 is 2,000, and we could cancel one of the pi's and cancel one of the r's. If I'm going to take the derivative of that, you might prefer, instead of 2,000 over r, you might prefer to write that as 2,000 r to the negative 1. All right, so if you take the derivative of 2000r to the negative 1, what are you going to get? Yes, negative 2000r to the negative 2. And if we take the derivative of 2 pi r squared, what will we get? 4 pi r. All right, so I've got negative 2000r to the negative 2. You could also write that as negative 2000 over r squared, if you'd rather. All right, so there's my derivative. So now I need to consider endpoints, and I need to consider critical numbers. All right, let's think about endpoints for just a second. Remember that it's in essence the domain of this unknown. In our case, it's r. So r is a radius. It can't be negative. The smallest value it could be would be 0 then, right? But hang on. Because in this problem, if r is 0, what would my volume be? 0. And they told me that my volume was 1,000. So that means r can't be 0. So it could be some value, you know, 0.0000001. It could be some itty bitty teeny tiny value, and then h would be some preposterously large value. But I can't be equal to 0. Happy days, because that means that you don't have a closed interval for this problem, and you won't have to check endpoints. So our work just got a whole lot easier. All right, so no endpoints. So now all I need to do is just consider critical numbers. Critical numbers are where my derivative equals 0 or it doesn't exist. Where does this derivative not exist? Where r is equal to 0, because I get 0 in the denominator. But we just had the whole discussion that 0 is not in our domain, so we can toss that. We won't have to worry about it. So all we need to concentrate on is then setting our derivative equal to 0. So I'm going to add that 200 over r squared to the other side. And then cross multiply or multiply both sides by r squared, whichever way you want to think of that. And then I need to get r by itself. So I'll divide by the 4 pi, and then I'll take the cube root. And I know we're supposed to give answers in exact terms, but if I'm going to make a sign graph, it's kind of hard to graph the cube root of 500 over pi, so I am going to go ahead and get a decimal for that, just so I can make my sign graph. All right, so I'm going to graph my derivative. The only critical number I got was 5.4. That does not mean that it is necessarily my minimum. I got to check. So let's pick a test point. 0 is not going to do me any good because we already discussed that up here. So I just chose 1. You could choose anything you want to. I'm going to take 1 and plug it back into what? The original or the derivative? The derivative, because it is a sign graph for the derivative. And I get a negative value. So if it is negative here across a single critical number, the sign changes. And anywhere my derivative changes from negative to positive, I have a minimum, right? So if that is the relative minimum and it is the only minimum and there are no endpoints to consider, then it also has to be my absolute minimum. And so again, for this problem, they asked me to give the dimensions. So I'm going to have an absolute minimum when this is my r value. And so I need to plug back in and find h. Again, I have a formula right up here for h that I can use. So if h is 1,000 divided by pi r squared, then I'm just going to replace r with that value we had gotten for it. Remember, I don't have to simplify that down for AP. I can leave it in that complex form.